Claudius Ptolemy, a figure whose name has echoed through the halls of scientific history, remains one of the most influential polymaths of antiquity. While much of his life is shrouded in mystery, his contributions to astronomy, geography, mathematics, and astrology have shaped the course of intellectual thought for centuries. Ptolemy was a Greek-speaking Egyptian, born in the city of Alexandria around the middle of the 2nd century CE, during the Roman Empire's reign over Egypt. Despite the uncertainty surrounding many aspects of his life, Ptolemy's scientific work remains pivotal in understanding the medieval and early modern worlds. This chapter aims to introduce the key aspects of Ptolemy's life and the environment in which his groundbreaking ideas flourished. Ptolemy lived at a time when the Roman Empire was at its zenith, yet his world was deeply influenced by the remnants of Greek philosophy and the intellectual traditions that had evolved over centuries. The Hellenistic period, which began with the conquests of Alexander the Great in the 4th century BCE, left behind a legacy of intellectual curiosity, especially in the domains of science and mathematics. Alexandria, the epicenter of Greek scholarship, was the perfect environment for Ptolemy to develop his ideas. It was here, in this cosmopolitan city, that Greek, Egyptian, and later Roman ideas converged, providing a fertile ground for intellectual exploration. The Library of Alexandria, the most famous repository of knowledge in the ancient world, is often cited as a major influence on scholars like Ptolemy. While there is no direct evidence that Ptolemy worked at the library, it is clear that he was part of the intellectual climate it fostered. The library and the associated museum were not merely places for the preservation of texts, but hubs of scientific and philosophical discourse. This milieu of inquiry, which included figures such as Euclid, Archimedes, and Hipparchus, laid the foundation for the systematic approach to science that would characterize Ptolemy's own work. In his own time, Ptolemy was a figure whose works were central to the academic community, though his reputation as a scientist would grow more prominent posthumously. The most famous of his works, the Almagest, was an astronomical treatise that became the authoritative source on astronomy in the Western world for over a millennium. His model of the cosmos, the geocentric or Ptolemaic system, placed the Earth at the center of the universe, surrounded by concentric spheres holding the moon, sun, planets, and stars. This model, though later displaced by the heliocentric theory of Copernicus in the 16th century, dominated scientific thinking for over 1,400 years, cementing Ptolemy's position in the history of science. Ptolemy's achievements were not limited to astronomy. In his Geographia, he created a comprehensive mapping of the known world, utilizing a grid system based on latitude and longitude. His work in geography introduced a more precise approach to cartography, an endeavor that would lay the groundwork for the future exploration and mapping of the globe. Ptolemy's methodology, which combined mathematical rigor with empirical observation, was revolutionary for its time. His contributions to the science of mapping would not be surpassed for centuries, influencing explorers and cartographers in both the Islamic and Western worlds. The influence of Ptolemy extended beyond the natural sciences into astrology, where he sought to systematize the practice of interpreting the positions of celestial bodies. His Tetrabiblos became a foundational text in astrological thought, blending astronomical observations with philosophical ideas. Ptolemy's view that the movements of the planets could influence human affairs resonated deeply with both the intellectual elites and the general public, making astrology a central feature of the intellectual landscape in both the ancient and medieval worlds. However, Ptolemy's work has not been without criticism. The geocentric model he developed was grounded in observation and mathematical precision, yet it was not entirely accurate. His system, like the Ptolemaic view of the universe, was eventually overthrown by the Copernican revolution. Despite this, Ptolemy's methodology, his approach to empirical evidence, and his commitment to mathematical reasoning influenced countless scientists and thinkers who followed him. His contributions were not easily dismissed. They continued to be utilized and modified as scientific understanding advanced. Another aspect of Ptolemy's intellectual legacy is his philosophical worldview. While he was primarily a scientist, Ptolemy's work also intertwined with the broader philosophical traditions of his time. His belief in the harmony of the universe, expressed in the intricate movements of the heavens, drew from the philosophical ideas of Plato and Aristotle. For Ptolemy, the cosmos was a perfect, orderly system that reflected a divine, rational order. This metaphysical view contributed to his authoritative stance in intellectual circles, where he was regarded as an authoritative figure in both scientific and philosophical matters. The Roman Empire, in which Ptolemy lived and worked, provided both opportunities and limitations for scientific inquiry. While the Roman Empire was a vast and sophisticated political entity, it was not particularly noted for fostering scientific advancements in the way that ancient Greece had done. However, Alexandria, though part of the Roman Empire, maintained its intellectual vigor, and it was here that Ptolemy was able to synthesize Greek, Egyptian, and Roman knowledge into his own remarkable works. The blending of these diverse intellectual traditions allowed Ptolemy to push the boundaries of what was known at the time, leaving a lasting imprint on the future of science. Ptolemy was not merely a man of his time, but a product of the intellectual and cultural currents of the Hellenistic and Roman worlds. His work, deeply informed by the scientific knowledge of his predecessors, would go on to influence not only the generations of scholars in his own time, but also those of the medieval and Renaissance periods. His contributions in astronomy, geography, and astrology, while subject to later revision, helped to shape the way humanity viewed the cosmos for centuries. Understanding the life and work of Ptolemy allows us to appreciate the complexity of the intellectual heritage that has shaped the development of modern science and philosophy. The early life of Claudius Ptolemy remains one of the most elusive aspects of his biography. Historical records provide no concrete details regarding his date of birth or his familial background. What is clear, however, is that Ptolemy was born during a pivotal time in the intellectual history of the ancient world, and his early years were undoubtedly shaped by the rich cultural environment of Alexandria. Ptolemy's life was situated in an era where intellectual inquiry flourished, particularly in the realms of astronomy, mathematics, and philosophy. His education and formative experiences in this environment would play a significant role in shaping the scientific contributions for which he would later become renowned. Ptolemy's exact birthplace is generally assumed to be Alexandria, a major intellectual hub under Roman control. Alexandria, located in Egypt, was famous for its library, one of the largest and most significant libraries of the ancient world. While there is no direct evidence that Ptolemy worked within the library itself, it is highly probable that he benefited from the academic resources and the intellectual climate that Alexandria provided. This city was home to a diverse group of scholars from various cultural backgrounds, including Greek, Egyptian, and Jewish thinkers, and it was here that Hellenistic science and philosophy found their most significant expression. For Ptolemy, being in such a city meant that he was exposed to the works of earlier luminaries like Euclid, Hipparchus, and Aristotle, who would all leave indelible marks on his thinking. The intellectual tradition that shaped Ptolemy was deeply rooted in Greek philosophy and mathematics. The works of Plato and Aristotle had a profound influence on the way that ancient thinkers viewed the world, especially in relation to the heavens and the natural order. Aristotle, for example, posited a geocentric view of the cosmos, which positioned the Earth at the center of the universe, surrounded by concentric spheres carrying the moon, sun, and planets. This idea would resonate with Ptolemy as he formulated his own astronomical theories, although his model would incorporate far more detailed mathematical observations. The mathematical approach of figures such as Euclid and Archimedes also would have been fundamental to Ptolemy's education, particularly in his understanding of geometry and the relationship between physical space and celestial motion. Ptolemy's exposure to the work of Hipparchus, the Greek astronomer who lived just before him, was perhaps the most influential in shaping his own astronomical framework. Hipparchus was instrumental in developing the first comprehensive star catalog, and his pioneering work in measuring the length of the year and the motions of the planets set the foundation for later developments in astronomy. Hipparchus' use of a geocentric model that incorporated epicycles, small circles in which planets moved while simultaneously orbiting a larger circle, served as a critical starting point for Ptolemy's own Almagest. While Ptolemy would build upon Hipparchus' work, his synthesis of these ideas into a more unified and mathematically precise system would mark a significant advancement in the field. Another key intellectual influence on Ptolemy's early years was the philosophical framework of the Stoics. Stoicism, which emphasized the rational order of nature and the belief in a divine intelligence that governed the cosmos, aligned well with Ptolemy's view of the universe. In his Almagest and other works, Ptolemy expressed the belief that the universe was governed by a rational and harmonious set of principles. His use of geometry and mathematics to explain the motions of the heavens reflected a Stoic view of an orderly, purposeful universe, one in which celestial events were not random, but rather part of a larger, divine design. This metaphysical perspective would be central to his work in both astronomy and astrology. Ptolemy's formative years would also have been marked by the intellectual exchange that characterized Alexandria in the 2nd century CE. This exchange was not limited to Greek thought alone, as Egyptian and Persian influences were deeply integrated into the intellectual fabric of the city. Egyptian priests and scholars, for instance, had long been concerned with the study of the stars, and the complex calendars and astronomical systems they developed would have influenced Ptolemy's understanding of time and the motion of the heavens. The blending of these various cultural traditions in Alexandria likely provided Ptolemy with a well-rounded foundation in both the scientific and philosophical practices of the day. While the classical Greek tradition of thought dominated Ptolemy's education, he was also aware of the ongoing Roman presence in Egypt. The Roman Empire, under whose rule Egypt fell, was not particularly noted for its contributions to scientific inquiry in the same way that earlier Greek or Hellenistic civilizations had been. However, the Romans placed great importance on the practical application of knowledge, especially in fields such as engineering, architecture, and military technology. This practical approach to knowledge may have influenced Ptolemy's method of systematizing his observations and theories in a way that could be applied to real-world problems, such as predicting celestial events or navigating the Earth's surface. Ptolemy's intellectual development would have been further guided by his exposure to the work of mathematicians and astronomers who were his contemporaries or predecessors in the broader Mediterranean world. It is likely that Ptolemy was familiar with the works of Roman mathematicians such as Geminus and Menelaus, who were instrumental in the study of spherical geometry and the mechanics of planetary motion. These mathematicians, alongside Greek scholars, helped to create a foundation of knowledge that Ptolemy could build upon. Through this academic network, Ptolemy was able to refine his own ideas and gain a deeper understanding of the complex phenomena he sought to explain. Despite the relatively little we know about Ptolemy's personal life, it is evident that he was deeply committed to empirical observation and mathematical rigor. This combination of practical observation with theoretical insight would be a hallmark of his work, especially in his contributions to astronomy and geography. Ptolemy's meticulous nature and attention to detail were essential for the development of the models and systems that would become the basis of his later works, such as the Almagest and Geographia. His ability to synthesize various strands of thought, whether from Greek philosophy, Egyptian astronomy, or Roman mathematics, demonstrates a mind capable of drawing connections across disciplines to create a cohesive and lasting body of work. Ptolemy's early life was marked by a confluence of intellectual traditions that set the stage for his later accomplishments. Growing up in Alexandria, a center of learning and cultural exchange, he was exposed to a wide range of ideas that shaped his approach to science and philosophy. His education in Greek philosophy, Egyptian astronomy, and Roman mathematics would form the intellectual bedrock upon which Ptolemy would build his scientific theories. This early exposure to a variety of intellectual currents helped to mold Ptolemy into the figure whose works would later influence generations of scholars, both in the classical world and in the Middle Ages. As we move forward in exploring his contributions to science, it becomes clear that Ptolemy's early experiences laid the foundation for a legacy that would shape the future of both Western and Islamic thought. The city of Alexandria, located at the mouth of the Nile in Egypt, was a beacon of intellectual and cultural exchange during the Hellenistic and Roman periods. Founded by Alexander the Great in 331 BCE, Alexandria quickly became one of the most important centers of learning in the ancient world. The city housed the famous Library of Alexandria, a vast repository of knowledge that attracted scholars from all corners of the Mediterranean world. Alexandria's blend of Greek Egyptian, and later Roman influences provided a rich intellectual environment for thinkers like Claudius Ptolemy. His association with Alexandria would be central to both his education and the development of his groundbreaking scientific works. Ptolemy's time in Alexandria, although not well documented, would have placed him at the heart of a flourishing intellectual and scientific community. By the time Ptolemy lived in the 2nd century CE, Alexandria was still one of the preeminent cities of learning in the Roman Empire. The city had been a focal point for scholars since the establishment of the library, which was renowned for housing tens of thousands of scrolls and manuscripts, many of which were the product of Greek philosophers, mathematicians, and scientists. Although the library's physical structure had suffered damage during the preceding centuries, Alexandria's role as an intellectual hub continued, attracting thinkers from all over the Roman Empire, including Ptolemy himself. It was in this vibrant intellectual climate that Ptolemy was able to refine his astronomical, mathematical, and geographical theories. Scholars from diverse backgrounds, including Greek philosophers, Egyptian astronomers, and Roman engineers, gathered in Alexandria to share knowledge and engage in intellectual debates. This confluence of intellectual traditions allowed Ptolemy to benefit from the accumulated knowledge of previous generations, while also contributing his own observations and insights to the broader scientific discourse. The city's academic atmosphere, steeped in Greek intellectualism and Egyptian tradition, provided Ptolemy with the tools and resources necessary for his academic pursuits. The Library of Alexandria, even after its destruction, continued to serve as a symbol of the intellectual legacy that Alexandria embodied. It is likely that Ptolemy had access to various scholarly works, many of which would have been preserved in Alexandria's vast collection. While Ptolemy's exact engagement with the library is unknown, it is clear that the city's intellectual network was critical to his development as a scholar. It is also important to note that Alexandria was home to the Museum, a research institution that attracted leading scientists and philosophers. The museum was not just a library. It was a place where scholars engaged in collaborative research and experimentation. Ptolemy, in this environment, would have had ample opportunities to study the works of previous astronomers, such as Hipparchus, and to engage with his contemporaries in scientific discussions. Ptolemy's deep involvement in astronomy is often tied to the intellectual traditions of ancient Greece. Yet his work would not have been possible without the influence of Egyptian astronomy. The Egyptians had a long-standing tradition of observing the stars and developing calendars based on celestial movements. Their astronomical knowledge, especially in relation to the timing of the annual flooding of the Nile, was sophisticated and deeply embedded in the culture. This knowledge, which was initially passed down orally, was later systematized and recorded in texts. Ptolemy, living in Alexandria, would have had access to this body of Egyptian astronomical knowledge, which likely shaped his understanding of celestial phenomena. Moreover, Ptolemy's familiarity with the Egyptian priestly traditions would have contributed to his methodical approach to science. In Egypt, priests had long been responsible for the observation of the heavens, often using detailed astronomical records to predict agricultural cycles. This practical, observational approach to science would have influenced Ptolemy's own methods. As a result, Ptolemy's astronomical models, such as the Ptolemaic system, were not merely theoretical constructs, but were grounded in the careful observation and measurement of celestial bodies. His integration of mathematical precision with astronomical observation became one of the hallmarks of his work, and this method would be further refined in the intellectual climate of Alexandria. In addition to astronomical and mathematical pursuits, Alexandria was a hub for the study of geography. Ptolemy's work in this field, especially his Geographia, was groundbreaking, and his exposure to the city's vibrant intellectual community was integral to his understanding of the world. Alexandria's position as a center of commerce, where goods from Africa, Asia, and Europe converged, made it an ideal place for the development of geographical thought. Ptolemy's use of a coordinate system based on latitude and longitude was an innovation that revolutionized the field of cartography. His methods would later influence both Islamic and European scholars, making Ptolemy one of the most important figures in the history of geography. The intersection of Greek and Egyptian knowledge in Alexandria also had philosophical implications. The city was a melting pot of ideas, where Greek philosophers such as Plato, Aristotle, and Euclid interacted with Egyptian religious and philosophical thought. The convergence of these traditions created a unique philosophical climate in Alexandria, which likely influenced Ptolemy's own worldview. For instance, Ptolemy's belief in the ordered nature of the cosmos, as exemplified in his geocentric model, reflects a Platonic and Aristotelian emphasis on the harmony and rationality of the universe. At the same time, Ptolemy's emphasis on empirical observation and mathematical rigor echoes the Egyptian tradition of careful measurement and record-keeping. Ptolemy's work in astrology, as exemplified in his Tetrabiblos, also demonstrates the influence of Alexandria's intellectual environment. Astrology in the ancient world was deeply intertwined with astronomy, and Alexandria's cosmopolitan nature provided fertile ground for the development of astrological thought. Ptolemy's approach to astrology was methodical and scientific, focusing on the mathematical relationships between celestial bodies and their potential influence on human affairs. This scientific approach to astrology was in contrast to the more mystical and speculative practices of earlier traditions, and it marked a significant development in the field. As Alexandria was a center for the synthesis of different cultural traditions, Ptolemy's work exemplifies the broader intellectual currents of his time. His ability to integrate Greek, Egyptian, and Roman ideas into a cohesive system was one of the defining features of his scholarship. Ptolemy's systematic approach to both the natural world and the human experience drew from diverse sources and was shaped by the pluralistic intellectual environment of Alexandria. It is this ability to bridge intellectual traditions that made his work so influential in the centuries that followed. Ptolemy's connection to Alexandria was fundamental to his development as a scholar and to the creation of his most influential works. The city's status as a center of learning, its blending of Greek, Egyptian, and Roman intellectual traditions, and its focus on empirical observation provided Ptolemy with both the resources and the intellectual climate to refine his ideas. It was in Alexandria that Ptolemy was able to synthesize the knowledge of the past and contribute his own discoveries to the ongoing conversation about the nature of the cosmos and the world. His work, influenced by the intellectual currents of the city, would go on to shape the scientific understanding of the medieval and Renaissance worlds, solidifying Alexandria's place as one of the most important intellectual centers in history. One of the most enduring legacies of Claudius Ptolemy is his development of the geocentric model of the universe, which became the dominant cosmological framework for over 1,400 years. Ptolemy's Almagest, written around 150 CE, presented a comprehensive and mathematically precise model of the cosmos, in which Earth was fixed at the center of the universe, with the sun, moon, planets, and stars revolving around it. This Ptolemaic system, sometimes referred to as the Ptolemaic universe, was not merely a scientific hypothesis, but a complex, systematic model that synthesized centuries of astronomical observation and mathematical reasoning. Although later displaced by the heliocentric model of Copernicus, the Ptolemaic system played a crucial role in shaping the way humanity understood the cosmos for more than a millennium. The geocentric model, or the Earth-centered view of the universe, was not an invention of Ptolemy, but rather a synthesis of earlier Greek astronomical thought, particularly that of Aristotle and Hipparchus. Aristotle had posited a spherical Earth at the center of the universe, with celestial bodies revolving around it in perfect, unchanging circles. Hipparchus, one of Ptolemy's intellectual predecessors, had also developed a geocentric model of the universe, though he had introduced the concept of epicycles, small circular orbits within larger ones, to explain the irregular motions of the planets. Ptolemy's contribution was to refine and systematize these ideas into a cohesive and predictive framework, adding mathematical precision that allowed for more accurate predictions of the positions of celestial bodies. In the Almagest, Ptolemy introduced a model of planetary motion based on a system of circles within circles. At the heart of this system was the concept of the deferent and the epicycle. The deferent was a large circle centered on the Earth, and within this, each planet was carried along a smaller circle, or epicycle. The planets were thought to move along these epicycles while simultaneously orbiting the Earth on the deferent, allowing Ptolemy to account for the observed retrograde motion of the planets. The inclusion of epicycles allowed Ptolemy's model to accurately describe the apparent irregularities in the motion of the planets, such as their temporary reversal of direction in the sky, which had perplexed astronomers for centuries. Ptolemy's system was groundbreaking in its ability to explain and predict the motions of the planets with remarkable accuracy for its time. By using mathematical methods to account for celestial motion, Ptolemy provided a model that could be applied not only to the known planets, but also to the stars and the moon. His work was based on the careful observation of the heavens, incorporating data from earlier astronomers like Hipparchus and other scholars who had measured the positions of stars and planets. In this way, Ptolemy's geocentric model was a product of both empirical observation and theoretical reasoning, combining the strengths of ancient Greek astronomy with the advanced mathematical tools of the time. The Ptolemaic system was not just a theoretical model. It was an astronomical tool that had practical applications. It provided a means of predicting the positions of celestial bodies with a high degree of accuracy, allowing for the development of detailed astronomical tables. These tables, which were based on the Ptolemaic model, became essential for navigation, calendrical calculations, and astrological predictions. The system's predictive power also made it a central feature of ancient and medieval astronomy, ensuring its continued relevance long after it was displaced by the heliocentric theory. Despite the success of the Ptolemaic model in predicting celestial motions, it was not without its flaws. The model, with its reliance on epicycles and deference, became increasingly complicated as astronomers tried to explain more detailed observations. As more planets were discovered and more data was gathered, the Ptolemaic system grew more elaborate, requiring additional layers of epicycles and adjustments to maintain its accuracy. This growing complexity led some critics to question the model's fundamental assumptions, as it appeared to be more of a patchwork of mathematical corrections than a true reflection of the cosmos. Nonetheless, the Ptolemaic system had a profound influence on subsequent generations of astronomers and scholars. For over 1,000 years, it was the dominant framework through which the universe was understood, not just in the Western world, but also in the Islamic world, where Ptolemy's works were studied, translated, and expanded upon. Islamic astronomers like al-Battani and Ibn al-Shatter made significant modifications to the Ptolemaic model, refining its calculations and improving its accuracy, yet the basic geocentric structure remained intact. The Ptolemaic system, with its precise predictions and mathematical rigor, was the foundation of astronomical thought in the medieval period. Ptolemy's geocentric model also played a central role in the development of astrology, which was tightly intertwined with astronomy in antiquity. For Ptolemy, the study of the movements of celestial bodies was not just a scientific pursuit, but also a means of understanding the influence of the heavens on earthly affairs. His Tetrabiblos, one of the most important works in the history of astrology, drew upon the geocentric model to explain how the positions and movements of the planets affected human lives. This view of the cosmos, with the Earth at the center and the planets exerting influence over human affairs, was deeply ingrained in both the scientific and cultural mindset of the ancient and medieval worlds. The Ptolemaic system's emphasis on a geocentric universe also reflected the philosophical and religious views of the time. The belief in the Earth's central position in the cosmos was seen as consistent with the idea that humans occupied a special, privileged place in the universe. In many ancient cultures, the Earth was viewed as the focal point of creation, with the heavens above representing divine order and perfection. The geocentric model reinforced this worldview, positioning humanity at the center of a harmonious and purposeful cosmos. This cosmological perspective was not only a scientific model, but also a theological and philosophical framework that influenced the development of Western thought for centuries. However, the Ptolemaic system was not to remain unchallenged forever. In the 16th century, the Copernican revolution would fundamentally alter the way the universe was understood. Nicholas Copernicus, a Polish astronomer, proposed a heliocentric model, placing the Sun at the center of the universe and the Earth in orbit around it. While Copernicus's theory was initially met with resistance, it eventually gained widespread acceptance, marking the beginning of a paradigm shift in scientific thought. The heliocentric model provided a simpler, more elegant explanation for the motions of the planets, and, in time, would be confirmed by the observations of astronomers such as Galileo Galilei and Johannes Kepler. Despite the eventual overthrow of the geocentric model, Ptolemy's work laid the groundwork for centuries of astronomical research and provided an indispensable tool for early modern astronomers. Ptolemy's geocentric model of the universe was one of the most significant achievements in the history of astronomy. It synthesized the astronomical knowledge of ancient Greece, refined by Ptolemy's own observations and mathematical techniques, into a cohesive system that was able to predict the positions of celestial bodies with remarkable accuracy. Although the model would later be supplanted by the heliocentric theory, it was the dominant cosmological framework for over 1,000 years, influencing both scientific and cultural thought. The Ptolemaic system's legacy, through its contributions to mathematics, astronomy, and astrology, continues to shape our understanding of the history of science and the development of the modern scientific method. While Ptolemy is primarily known for his groundbreaking work in astronomy, his contributions to the field of geography were equally influential and far-reaching. His Geographia, written in the 2nd century CE, is one of the earliest and most comprehensive works on the science of map-making and spatial understanding. The text, which compiled and expanded upon the geographical knowledge of the time, introduced innovative ideas that would shape the future of cartography and geographical exploration for centuries. Ptolemy's approach to geography, particularly his use of latitude and longitude, laid the foundation for modern geographical and cartographic methods and provided a framework for mapping the known world. The Geographia was Ptolemy's attempt to compile the knowledge of the known world based on the available geographic data of the time. It was a synthesis of information gathered from various explorers, scholars, and previous works, including those of earlier Greek geographers such as Eratosthenes and Hipparchus. While many of the geographical concepts in the Geographia were drawn from earlier sources, Ptolemy's true contribution lay in his systematic approach to organizing and presenting this knowledge. His method of dividing the world into a grid system using latitude and longitude would prove to be revolutionary, creating a way to represent the Earth's surface that would be employed for centuries to come. The system of latitude and longitude was not entirely new. Eratosthenes had previously used parallels and meridians in his work, but Ptolemy refined and popularized the concept. He divided the world into a series of latitudes, measuring the distance north and south of the equator, and longitudes, measuring east and west from a prime meridian. Ptolemy's system of coordinates was used to pinpoint locations on a map with remarkable precision. This concept of a global coordinate system would become a cornerstone of modern cartography and navigation. Although the accuracy of Ptolemy's coordinates was limited by the geographical data available to him, his system represented a significant advancement in the understanding of Earth's geometry. The Geographia also included a detailed description of the known world, including the regions of Europe, Asia, and Africa. Ptolemy's work featured maps that were based on the coordinates he had calculated, as well as written descriptions of various regions, peoples, and cultures. His maps, although far from perfect by modern standards, represented an ambitious attempt to present the Earth's surface in a way that was both systematic and comprehensible. Ptolemy's maps were some of the first to attempt a large-scale, comprehensive depiction of the world, and they set a precedent for future explorers and cartographers. However, Ptolemy's maps were not without their limitations. The geographical knowledge of his time was incomplete, and many of the maps he created were based on inaccurate or speculative information. For instance, the locations of various regions, such as parts of India and the Far East, were based on reports from explorers and merchants, which were often vague and inconsistent. As a result, many of Ptolemy's maps contained distortions or inaccuracies. For example, his depiction of the Indian Ocean was problematic, as he believed that the Indian subcontinent extended much farther east than it actually did. Despite these errors, Ptolemy's work was incredibly influential, and his maps remained the standard for centuries, being used by scholars and explorers throughout the medieval period and into the Renaissance. Ptolemy's Geographia also introduced the concept of projecting a three-dimensional globe onto a two-dimensional surface, which became an important feature of later mapmaking. His use of projections to represent the spherical Earth on flat maps was an innovative approach to cartography, although it was not without its flaws. The difficulty of accurately representing the curved surface of the Earth on a flat map led to various distortions, particularly in the depiction of areas far from the equator. Nevertheless, Ptolemy's use of projections represented an important step in the evolution of cartography, as it allowed for a more systematic and standardized way of representing geographical data. In addition to his work on geography, Ptolemy's contributions to the field of navigation were also significant. The coordinates he devised for mapping the Earth allowed for more accurate navigation, both on land and at sea. The use of latitude and longitude became a critical tool for sailors and explorers, enabling them to navigate across vast distances with greater precision. Although Ptolemy's methods were eventually replaced by more accurate ones in later centuries, his contributions to navigation were vital for the development of exploration and trade during the medieval and Renaissance periods. Ptolemy's Geographia also had a profound impact on Islamic scholars, who translated his work into Arabic and preserved it during the Middle Ages. Islamic geographers such as Al-Idrisi and Ibn Haqil drew heavily from Ptolemy's ideas and expanded upon them. These scholars were instrumental in preserving Ptolemy's geographical knowledge, as well as in refining and improving upon his maps. The work of these Islamic scholars would later influence European Renaissance cartography, creating a bridge between Ptolemy's ancient ideas and the new age of exploration that emerged in the 15th and 16th centuries. The Geographia's influence also extended to medieval Europe, where it played a crucial role in the development of European mapmaking. After the fall of the Roman Empire, much of the scientific knowledge of the ancient world was lost or forgotten. However, Ptolemy's work was rediscovered and translated into Latin during the 15th century, sparking a renewed interest in ancient Greek and Roman knowledge. Ptolemy's maps and geographic methods were influential in shaping the course of European exploration, as they provided a model for later cartographers and explorers. The accuracy of Ptolemy's geographical data was enhanced with new discoveries, as the age of exploration brought new information about the world's geography. Despite the imperfections in Ptolemy's maps and the inaccuracies of his geographical data, his Geographia remains one of the most significant works in the history of cartography. Ptolemy's systematic approach to mapping, his use of coordinates, and his methods for projecting the Earth onto flat maps were revolutionary for their time. His work laid the foundation for the development of modern cartography and navigation, and it continued to be used as a reference for centuries. In many ways, Ptolemy's Geographia is a testament to the intellectual achievements of the ancient world and a precursor to the scientific advances that would follow in the Renaissance and beyond. Ptolemy's contributions to geography and cartography were profound and far-reaching. His Geographia represented a significant advancement in the understanding of the Earth's surface and the creation of accurate maps. Ptolemy's use of latitude and longitude, his system of projections, and his synthesis of geographical knowledge from earlier scholars set the stage for the future of map-making and exploration. Although his maps contained inaccuracies, Ptolemy's work was a remarkable achievement that influenced scholars and explorers for centuries. His legacy in the field of geography endures, as his ideas continue to shape our understanding of the world. The impact of Claudius Ptolemy's works extended far beyond his own time, shaping the intellectual landscape of both the medieval and Renaissance periods. His astronomical and geographical writings were preserved, studied, and disseminated through the centuries, becoming central to the development of European and Islamic thought. The longevity and influence of Ptolemy's contributions can be traced through the careful transmission of his texts, as well as through the ways in which his ideas were adapted, modified, and at times challenged by later scholars. In this chapter, we will examine how Ptolemy's legacy endured through the Middle Ages and the Renaissance, influencing not only scientific thought, but also the broader cultural and intellectual movements of these periods. During the early Middle Ages, much of the scientific knowledge of the ancient world, including Ptolemy's writings, was lost or relegated to the margins of intellectual life in Europe. However, Islamic scholars played a crucial role in preserving and advancing the works of ancient Greek scientists and philosophers. Beginning in the 8th century, scholars in the Islamic world began translating the Greek texts into Arabic, including the works of Ptolemy, especially the Almagest and Geographia. This process of translation and preservation was integral to the survival of Ptolemy's ideas, which were then studied, debated, and expanded upon by Islamic scholars. Among the most important figures in the Islamic world who engaged with Ptolemy's work was al-Battani, an astronomer and mathematician whose observations and refinements of the Ptolemaic system advanced the field of astronomy. Al-Battani not only confirmed Ptolemy's calculations, but also corrected certain inaccuracies, making the Ptolemaic model more precise. His work influenced later European astronomers, and Ptolemy's system continued to be a cornerstone of Islamic astronomy for centuries. Other Islamic scholars, such as al-Farghani and Ibn al-Shatir, also made significant contributions to the development of the Ptolemaic system, demonstrating the ongoing relevance of Ptolemy's work in the medieval Islamic intellectual tradition. The transmission of Ptolemy's works into Europe occurred primarily through the Iberian Peninsula, where Arabic translations were made available to Latin-speaking scholars in the 12th and 13th centuries. The translations of Ptolemy's Almagest and Geographia were part of the broader Renaissance of learning in Europe, known as the Renaissance Carolingian, which was fueled by the rediscovery of ancient texts. The 12th century saw the translation of key astronomical and geographical works, and Ptolemy's influence in Europe was revitalized as his texts became central to the curriculum of medieval universities. The rediscovery of Ptolemy's Almagest in Latin had a significant impact on the study of astronomy during the late Middle Ages. The Almagest was considered the definitive astronomical text for centuries, and it remained the authoritative work in the field of astronomy for European scholars. Ptolemy's model of the universe, with its geocentric structure and mathematical precision, was accepted as the best explanation of celestial motion for the medieval scholars. His system, with its use of epicycles and deference, was seen as a way to reconcile the apparent irregularities in the movements of the planets with the belief in a perfect, unchanging cosmos. Throughout the medieval period, Ptolemy's geocentric model provided a foundation for not only astronomical studies, but also for the broader intellectual framework that governed the understanding of the universe. The notion of an Earth-centered cosmos, with the celestial bodies moving in harmonious, circular orbits, fit well with the theological and philosophical views of the time. The geocentric model reinforced the idea that the Earth and humanity occupied a special, central place in the divine order of the universe. This worldview, rooted in the philosophy of Aristotle and Ptolemy, was central to medieval scholasticism and was embraced by many Christian scholars who saw the heavens as a reflection of God's perfection. In addition to its influence on astronomy, Ptolemy's Geographia was also rediscovered in the medieval period, helping to shape the course of exploration and map-making. The geographical coordinates and the system of latitude and longitude that Ptolemy introduced allowed for a more precise representation of the world on maps. This concept was adopted and expanded upon by later European cartographers, and Ptolemy's work became an essential resource for travelers and explorers. His maps, though limited by the knowledge of the time, provided a framework for understanding the world and laid the groundwork for the geographical explorations that would define the age of exploration. The influence of Ptolemy on Renaissance thought is perhaps most evident in the intellectual revival that characterized the period. The Renaissance was marked by a renewed interest in the classical texts of ancient Greece and Rome, and the works of Ptolemy were among the most influential of these texts. In the 15th and 16th centuries, scholars began to reassess the Ptolemaic system and explore alternatives to the geocentric model. The heliocentric theory of Copernicus, which proposed that the sun, rather than the Earth, was the center of the universe, was one such challenge to Ptolemy's cosmology. Nevertheless, Ptolemy's Almagest continued to be an important reference for astronomers, even as they began to question its validity. The influence of Ptolemy during the Renaissance can also be seen in the work of the great astronomer Johannes Kepler, whose laws of planetary motion were crucial to the development of modern astronomy. Kepler, although working within the framework of Copernicus's heliocentric model, was deeply influenced by Ptolemy's mathematical methods and his emphasis on empirical observation. Ptolemy's work, even though ultimately superseded by later discoveries, provided the foundation for the astronomical revolution that unfolded in the Renaissance. Despite the rise of the heliocentric model and the eventual displacement of Ptolemy's geocentric system, the influence of his work did not fade entirely. In fact, the challenge to Ptolemy's cosmology marked a turning point in the history of science, as it led to the development of new methods of scientific inquiry and experimentation. Ptolemy's focus on observation, calculation, and mathematical modeling would become key elements of the scientific method, laying the groundwork for the later advancements of figures like Galileo and Newton. The very questioning of Ptolemy's ideas was a sign of the growing shift toward empirical science, where theories were subject to scrutiny and testing. In the realm of cartography, Ptolemy's contributions continued to be recognized and used for centuries after his death. During the Age of Exploration, European navigators and mapmakers relied on Ptolemy's methods to create more accurate maps of the newly discovered lands. His grid system of coordinates helped explorers plot their courses and navigate the seas, and his maps, though outdated by modern standards, served as an important reference for early explorers such as Christopher Columbus and Vasco da Gama. The influence of Claudius Ptolemy on the medieval and Renaissance worlds cannot be overstated. His astronomical and geographical works provided a foundation for centuries of scientific inquiry, and his ideas shaped the way scholars and explorers understood the cosmos and the Earth. Through the preservation and study of his works in the Islamic world and later in Europe, Ptolemy's intellectual legacy endured well into the Renaissance. His contributions to astronomy, geography, and cartography were instrumental in the development of modern science, and his influence can still be felt today in the methods and ideas that continue to shape scientific thought. The scientific revolution that unfolded in the 16th and 17th centuries marked a profound transformation in human understanding of the cosmos and the natural world. It was a period characterized by the questioning of long-held beliefs, the development of new scientific methods, and the emergence of groundbreaking theories that would ultimately challenge the Aristotelian and Ptolemaic frameworks that had dominated Western thought for over a millennium. At the heart of this revolution was the displacement of the geocentric model of the universe, which had been championed by Ptolemy and his Almagest and was entrenched in both scientific and theological thought. This chapter explores the gradual decline of Ptolemaic theory during the scientific revolution, focusing on the key figures, discoveries, and philosophical shifts that contributed to the collapse of the geocentric worldview. Ptolemy's geocentric model, which posited that the Earth was the center of the universe and that all celestial bodies revolved around it in intricate, circular orbits, had dominated Western astronomy for over 1,400 years. This system, although far from perfect, was highly influential, offering a mathematically sophisticated way of explaining the apparent movements of the planets and stars. It was a model that fit neatly with religious and philosophical beliefs of the time, particularly the notion that Earth was the center of God's creation. Thus, for centuries, Ptolemy's ideas remained largely unchallenged, even as the intellectual climate of Europe evolved and new discoveries were made. The first cracks in the Ptolemaic system appeared during the Renaissance, as astronomers and scholars began to question its accuracy. The introduction of the heliocentric model, proposed by the Polish astronomer Nicholas Copernicus in 1543, marked a pivotal moment in this process. Copernicus suggested that the Sun, rather than the Earth, was the center of the universe, and that the Earth and other planets orbited around it. While Copernicus' heliocentric model was not immediately accepted, largely because it contradicted religious teachings and lacked definitive empirical evidence, it offered a more elegant and mathematically simpler explanation for the motions of the planets than the complex epicycles and deferents that were used in the Ptolemaic system. Copernicus' ideas were revolutionary, but they did not immediately dismantle the Ptolemaic framework. The lack of sufficient observational evidence for the heliocentric model, coupled with the deeply entrenched religious and philosophical commitment to a geocentric view of the universe, meant that Ptolemy's ideas continued to hold sway for much of the 16th century. Nonetheless, Copernicus' work laid the groundwork for further astronomical inquiry, and it sparked a new wave of interest in challenging traditional astronomical thought. Copernicus' heliocentric theory gained traction among a small group of astronomers, including the German mathematician and astronomer Johannes Kepler, who would go on to make important contributions that would further undermine the Ptolemaic system. Kepler's work in the early 17th century represented a critical step forward in the rejection of Ptolemaic theory. Initially a proponent of the Copernican model, Kepler sought to refine and improve it by using empirical data to calculate the orbits of the planets. Through his meticulous analysis of the observations made by the Danish astronomer Tycho Brahe, Kepler discovered that the planets did not follow circular orbits, as had been assumed in the Ptolemaic system, but rather elliptical ones. This groundbreaking realization, which became known as Kepler's first law of planetary motion, was a direct challenge to the Ptolemaic model's reliance on perfect circles as the basis of planetary orbits. Kepler's work had profound implications for the understanding of the universe. By replacing circular orbits with elliptical ones, he not only improved the accuracy of planetary predictions, but also set the stage for a new approach to celestial mechanics. Kepler's discovery of elliptical orbits shattered the Ptolemaic belief in the perfection of celestial bodies, which had been a key feature of ancient cosmology. Furthermore, Kepler's work helped to confirm the Copernican model, providing empirical evidence that supported the idea that the Earth and other planets revolved around the Sun. While Kepler was refining the Copernican model, another major figure in the scientific revolution, Galileo Galilei, was making groundbreaking contributions that further undermined Ptolemy's geocentric theory. Galileo's use of the newly invented telescope in the early 17th century allowed him to make observations of the heavens that had never been possible before. His discoveries, such as the moons of Jupiter, the phases of Venus, and the rugged surface of the moon, provided direct evidence that not all celestial bodies revolved around the Earth. Galileo's observations also revealed that the Sun had spots, which contradicted the Ptolemaic and Aristotelian belief that celestial bodies were perfect and unchanging. In addition to his astronomical discoveries, Galileo's support for the heliocentric model led to a direct confrontation with the Catholic Church, which upheld the Ptolemaic model as part of its religious doctrine. Galileo's advocacy for the Copernican system eventually led to his trial by the Inquisition in 1633, where he was forced to recant his views. Despite this, Galileo's work remained immensely influential, and his observations helped to solidify the heliocentric model as a viable scientific theory. Galileo's telescopic observations, combined with Kepler's laws of planetary motion, effectively rendered the Ptolemaic model obsolete. As the 17th century progressed, the final nail in the coffin of Ptolemaic astronomy came with the work of Isaac Newton. Newton's Philosophiae Naturalis Principia Mathematica, published in 1687, provided a comprehensive and mathematical framework for understanding the motions of celestial bodies. Using Kepler's laws and Galileo's observations, Newton formulated his law of universal gravitation, which explained the forces that govern the motion of planets and other objects in space. Newton's theory offered a unified, mathematically rigorous model of the universe that not only confirmed the heliocentric system, but also explained the underlying physical forces at work in celestial and terrestrial motion. Newton's synthesis of earlier work by Copernicus, Kepler, and Galileo, along with his own groundbreaking contributions, represented the culmination of the scientific revolution. His laws of motion and gravity provided a comprehensive understanding of the universe that replaced the Ptolemaic system once and for all. Newton's work marked the end of the geocentric model that had been championed by Ptolemy, and his scientific achievements paved the way for the modern understanding of physics, astronomy, and the natural sciences. The decline of Ptolemaic theory was not simply a matter of scientific progress. It also reflected deeper shifts in philosophical and cultural attitudes. The scientific revolution was marked by a growing emphasis on empirical observation, experimentation, and mathematical reasoning. These values, which would come to define modern science, contrasted sharply with the medieval reliance on authority, tradition, and theological interpretation. Ptolemy's system, with its reliance on complex mathematical models and its alignment with religious doctrines, was increasingly seen as an outdated and inadequate explanation of the cosmos. In contrast, the heliocentric model and the new scientific methods offered a more dynamic and empirical way of understanding the universe. The decline of Ptolemaic theory was a gradual but profound process that culminated in the scientific revolution of the 16th and 17th centuries. Copernicus, Kepler, Galileo, and Newton each contributed to the dismantling of the geocentric model by providing new insights and evidence that contradicted Ptolemy's cosmology. The shift from a geocentric to a heliocentric understanding of the universe marked a turning point in human intellectual history, laying the foundation for modern science and changing forever the way humanity viewed its place in the cosmos. Ptolemy's intellectual contributions, particularly in the fields of astronomy and geography, have left an indelible mark on modern scientific thought. Despite the decline of his geocentric model with the rise of heliocentrism and the development of new theories of planetary motion, the legacy of Ptolemy's work is far from diminished. His innovative methods, attention to empirical observation, and mathematical approach to understanding the natural world continue to influence contemporary science. In this chapter, we explore Ptolemy's enduring impact on modern astronomy and geography, examining how his ideas, methods, and frameworks have shaped and informed the fields even as new theories have supplanted his original models. Ptolemy's Almagest, though eventually superseded by the heliocentric model, remains one of the most important works in the history of astronomy. The Almagest introduced an elaborate system of epicycles and deference to explain the apparent motions of the planets. This mathematical framework, despite its inaccuracies, provided a model that was influential for over a millennium. It also introduced the notion that celestial movements could be understood through a combination of geometry and observation, a principle that would persist in the scientific method. While the Ptolemaic system was eventually abandoned, the techniques it introduced, such as the use of mathematical models to describe celestial phenomena, laid the groundwork for future advancements in astronomy. Even as the heliocentric model displaced the Ptolemaic system, Ptolemy's rigorous approach to measurement and observation was not discarded. In fact, it became a cornerstone of future astronomical inquiry. His ability to calculate the positions of stars and planets with remarkable precision for his time was an achievement that would inspire later astronomers. Johannes Kepler, for instance, was heavily influenced by Ptolemy's mathematical methods, even as he moved toward a new understanding of planetary motion. While Kepler's elliptical orbits departed from the circular paths proposed by Ptolemy, Kepler's reliance on Ptolemaic mathematics to refine his own theories underscores the lasting value of Ptolemy's contributions to the development of scientific thought. Moreover, Ptolemy's insistence on empirical observation influenced future scientific practices. His work in the Almagest was based on detailed observations of the night sky, some of which were conducted over many years. While his instruments and techniques were rudimentary by today's standards, his commitment to using data to build his astronomical models set an important precedent for later scientists. The importance of accurate, systematic observation would become a central tenet of the scientific revolution and remains a foundational principle in modern astronomy. It is through this method of observation, interpretation, and mathematical modeling that modern astronomers continue to map the stars and planets. Ptolemy's Geographia, which presented a detailed map of the known world, was another work that would shape future scientific endeavors. Although many of his geographical ideas were based on inaccurate or incomplete information, such as his estimation of the size of the Earth, his approach to mapping and the organization of geographical knowledge would remain influential for centuries. His use of a grid system to denote latitude and longitude was a revolutionary concept that formed the basis of modern cartography. Today, the system of geographic coordinates that Ptolemy introduced is still in use, albeit with much more accurate measurements and refined technology. However, Ptolemy's fundamental approach to representing the world on a flat surface continues to underpin modern geographic and navigational systems. The impact of Geographia was particularly evident during the Age of Exploration. European explorers like Christopher Columbus and Vasco da Gama, who sought new trade routes to Asia and the Americas, used Ptolemy's maps as reference points. While Ptolemy's understanding of the world was limited and based on incomplete knowledge, the grid system he developed allowed explorers to chart their courses with greater precision than had previously been possible. As such, Ptolemy's geographic contributions were integral to the success of these explorations and to the expansion of European global influence during the Renaissance. Ptolemy's geographical work also paved the way for the development of more accurate and detailed maps during the subsequent centuries. While many of the details of his maps have since been corrected, such as the inaccurate portrayal of the size and shape of the continents, his overall system of geographic coordinates and his methodical approach to cartography were foundational. In the 16th century, when European explorers were making new discoveries and mapping the Americas, Ptolemy's methods remained integral to the creation of more precise maps. Cartographers such as Gerardus Mercator would build upon Ptolemy's ideas, adapting and refining them to suit the needs of the emerging global age. Even in modern times, Ptolemy's influence on geography persists. The use of latitude and longitude, a direct legacy of Ptolemy's grid system, is fundamental to navigation and geographic information systems, GIS. The global positioning systems, GPS, that are now commonplace in everyday life owe much of their conceptual framework to the system of coordinates that Ptolemy introduced. The ability to map the world in a systematic and consistent manner, using a coordinate grid to determine exact locations on the Earth's surface, is an advancement that traces its roots back to Ptolemy's work. In astronomy, Ptolemy's legacy is also evident in the ongoing process of cataloging and studying celestial bodies. Modern astronomers continue to use precise calculations and measurements to track the positions of stars and planets, much like Ptolemy did in his time. While the understanding of the universe has vastly expanded since Ptolemy's era, his pioneering work in cataloging the stars and developing a framework for understanding planetary motion laid the foundations for the sophisticated models used by astronomers today. The modern star cataloging systems, though vastly more advanced and accurate, still bear the influence of Ptolemy's pioneering efforts in mapping the heavens. One of the most important aspects of Ptolemy's legacy is his role in the development of the scientific method. While he was not the first to use observation and mathematical modeling, his integration of these techniques into the study of astronomy and geography set an example for future scientists. Ptolemy's work was grounded in the idea that the natural world could be understood through systematic observation, measurement, and calculation, an approach that would become a hallmark of the scientific method in the centuries to come. This method of inquiry, emphasizing data collection, hypothesis testing, and mathematical modeling, continues to drive the progress of science and technology. While Ptolemy's theories of astronomy and geography have been superseded by more accurate models, his legacy remains deeply ingrained in modern science. His contributions to the development of the scientific method, his use of mathematical models, and his innovative work in mapping the world and the heavens have had a lasting influence on both astronomy and geography. From the use of coordinates in modern maps to the methods of empirical observation in astronomy, Ptolemy's ideas continue to shape the ways in which we understand and navigate the natural world. Despite the advances of subsequent generations of scientists, Ptolemy's work remains an essential part of the history of science, demonstrating how ideas, even those that are ultimately replaced, can have a lasting impact on the future of human knowledge. The intellectual landscape of the Middle Ages and the Renaissance was profoundly shaped by the works of classical scholars, including Ptolemy, whose ideas in astronomy and geography continued to dominate scholarly thought well into the early modern period. Despite the intellectual ferment of the Renaissance, which saw the rediscovery of ancient Greek and Roman texts and the rise of humanism, Ptolemy's works remain central to both medieval and Renaissance scholars. This chapter examines how Ptolemy's theories were integrated into the intellectual frameworks of the Middle Ages and the Renaissance, exploring how his geocentric model and geographic ideas influenced not only the sciences, but also the broader philosophical and theological discourse of the time. During the Middle Ages, Ptolemy's Almagest was regarded as the authoritative text on astronomy. Its geocentric model, which placed the Earth at the center of the universe, was embraced by scholars and theologians as it aligned with the prevailing religious worldview. In the Christian context, Ptolemy's model was seen as harmonious with the belief that humanity occupied a central place in God's creation. The Church, which was the dominant intellectual authority of the time, endorsed Ptolemy's ideas, considering them to be divinely inspired. Consequently, Ptolemy's system was not only accepted but integrated into the theological discussions of the period, and it played a crucial role in shaping medieval cosmology. In the medieval period, Ptolemy's Geographia was equally influential. The map of the world that Ptolemy created based on the geographical knowledge of his time, provided the framework for medieval cartography. Ptolemy's work, though incomplete and occasionally inaccurate by modern standards, was a valuable tool for European scholars. His use of coordinates and the system of latitude and longitude, though primitive, was groundbreaking and would have long-lasting effects on the development of geographic knowledge. The Geographia remained a primary source for medieval maps, and many of the key ideas that emerged from his work were incorporated into later geographical studies, especially as European exploration expanded in the late medieval period. One of the most significant ways in which Ptolemy influenced medieval thought was through his work's synthesis of Greek and Roman knowledge. The Almagest was not merely a work of astronomy, but a comprehensive treatise that built upon the works of earlier astronomers, including Hipparchus. Ptolemy's synthesis of their ideas into a unified system provided a foundation for future scholarship, especially in the Christian intellectual tradition. His integration of astronomical theory with philosophical and theological frameworks allowed for the continuation of classical learning through the medieval period, which was crucial for the preservation and transmission of knowledge during the so-called Dark Ages. As Europe transitioned into the Renaissance, Ptolemy's works were rediscovered and became part of the intellectual revival that characterized the period. Humanist scholars who sought to recover and study the classical texts of antiquity embraced Ptolemy's contributions as part of their broader efforts to revive ancient learning. However, while Renaissance thinkers admired Ptolemy's scholarship and the mathematical rigor of his astronomical theories, they also began to question the assumptions that underpinned his models. The rediscovery of his works led to an era of intellectual experimentation in which his ideas were both celebrated and critiqued, as scholars sought to reconcile the findings of the ancient world with the emerging new scientific methods of the Renaissance. One of the key figures in this intellectual shift was the Polish astronomer Nicholas Copernicus, whose heliocentric theory ultimately supplanted Ptolemy's geocentric model. However, it is important to note that Copernicus was not rejecting Ptolemy's work outright. Rather, he built upon it. Copernicus acknowledged Ptolemy's contribution to astronomy and used his mathematical methods as the basis for his own system. In fact, the De Revolutionibus Orbium Coelestium, 1543, Copernicus' seminal work, was largely framed within the context of Ptolemaic astronomy, and Copernicus' heliocentric model represented an extension and refinement of the Ptolemaic approach rather than a complete rejection of it. Thus, while Copernicus' work signified a profound break with the past, it was also a continuation of Ptolemy's intellectual legacy. The rise of the heliocentric model during the Renaissance did not mean that Ptolemy's influence was immediately erased. Instead, his ideas continued to hold sway in the scientific and intellectual discourse of the period. Even after the Copernican Revolution, astronomers such as Johannes Kepler and Galileo Galilei, who championed the heliocentric model, were influenced by Ptolemy's methods. Kepler, for example, employed Ptolemaic mathematics in his work on planetary motion, using the tools of celestial observation and calculation that Ptolemy had pioneered. Similarly, Galileo's telescopic discoveries were often interpreted in the context of Ptolemaic theory before the full implications of his findings were understood. Thus, Ptolemy's work was integral to the development of Renaissance astronomy, even as it was gradually supplanted by new models. In addition to the direct influence on astronomy, Ptolemy's work in geography remained an essential part of Renaissance thought. As European explorers set out to chart new lands and establish global trade routes, Ptolemy's system of coordinates provided an important framework for navigation. His concept of a spherical Earth, though rudimentary by modern standards, helped shape Renaissance cartography and the early development of global maps. Renaissance mapmakers such as Gerardus Mercator drew upon Ptolemy's methods to create increasingly accurate maps of the world, incorporating both new discoveries and the geographical principles outlined in the Geographia. These maps were crucial in guiding explorers, traders, and navigators as they ventured into unknown territories. Moreover, Ptolemy's influence extended beyond the sciences into the realm of philosophy and theology. Throughout the Middle Ages and Renaissance, his geocentric model was seen as more than a scientific theory. It was also an integral part of the philosophical and theological worldview. The idea that Earth was the center of the universe resonated with the Christian notion of humanity's special place in the cosmos, and Ptolemy's model provided a harmonious framework that supported this belief. The eventual collapse of the Ptolemaic system, driven by the rise of the heliocentric model, had significant implications not only for astronomy, but also for broader philosophical and theological thought. It marked a shift in human self-understanding, as the realization that Earth was not the center of the universe forced a re-evaluation of humanity's place in the grand scheme of creation. Ptolemy's enduring influence also extended to the development of scientific institutions during the Renaissance. The rediscovery of his work contributed to the establishment of observatories, astronomical societies, and universities that were dedicated to advancing knowledge of the natural world. His emphasis on the empirical collection of data and the application of mathematics to scientific problems laid the intellectual foundations for the institutionalized study of astronomy and geography. Institutions such as the University of Padua and the Royal Observatory in Greenwich would continue to build on Ptolemy's legacy as they fostered the development of modern science. Ptolemy's influence on medieval and Renaissance thought was profound and enduring. His work in both astronomy and geography shaped the intellectual and scientific frameworks of the time, even as his models were eventually challenged by new discoveries and theories. The integration of Ptolemy's ideas into the intellectual currents of the Middle Ages allowed for the preservation of ancient knowledge and its transmission to future generations. In the Renaissance, Ptolemy's works were rediscovered, critiqued, and reinterpreted, providing both a foundation for new scientific ideas and a lens through which to examine the rapidly changing world. Ultimately, Ptolemy's legacy was not only in the geocentric model that he proposed, but in the methodological rigor and intellectual curiosity that he instilled in future generations of scholars. His contributions remain a key chapter in the history of science and philosophy, illustrating the complex relationship between past knowledge and future discoveries. Ptolemy's influence, though originating in the ancient world, continues to reverberate in contemporary intellectual thought across a wide range of disciplines. While many of his specific astronomical and geographical models have been superseded by more accurate theories, the core principles he introduced remain relevant in the ongoing development of scientific methods. In this final chapter, we explore how Ptolemy's legacy is sustained in modern times, examining the continuing relevance of his ideas in areas such as scientific methodology, education, and even cultural and philosophical contexts. Although his specific models are no longer in use, Ptolemy's intellectual contributions offer important lessons on the progression of scientific knowledge and the ways in which humanity approaches the mysteries of the universe. Ptolemy's primary legacy is perhaps his methodological approach to scientific inquiry. His work in astronomy, particularly in the Almagest, set a precedent for future scientific models by combining observation, measurement, and mathematical theory. The idea that the cosmos could be understood through rigorous observation and mathematical abstraction was revolutionary in its time and laid the groundwork for the later development of the scientific method. Modern science continues to rely on these core principles, where empirical data is collected, analyzed mathematically, and used to refine or challenge existing models. In this way, Ptolemy's methods represent the foundation of the empirical tradition that is central to contemporary scientific practice. One of the most enduring aspects of Ptolemy's methodology is his insistence on integrating observation with theoretical models. While Ptolemy's geocentric model was later replaced by the heliocentric theory, his work set an important example of how theories must be tested and adjusted based on empirical data. This iterative process of testing hypotheses, gathering new data, and adjusting theories accordingly remains the hallmark of modern science. Today's astronomers, physicists, and other scientists still rely on this process of refining models and theories based on new observations, whether it's tracking the motions of distant stars or analyzing the behavior of subatomic particles. The value of observation-driven theory, which Ptolemy championed, continues to be central to the scientific enterprise. Ptolemy's influence can also be seen in the educational world. In the centuries following his death, his works were essential parts of the curriculum in medieval and Renaissance universities. Even in the early stages of modern science, Ptolemy's Almagest and Geographia were considered foundational texts in the study of astronomy and geography. Today, Ptolemy's influence is still present in the way scientific and geographic knowledge is transmitted to students. Although the specifics of his models are no longer taught as factual representations of the cosmos, the historical significance of his contributions is acknowledged in academic settings. His work is a touchstone for understanding the evolution of scientific thought and serves as an important example of how knowledge can progress through successive models and theories. Moreover, Ptolemy's work in cartography and geography continues to be of historical significance. His contributions to the conceptualization of the Earth and the use of coordinate systems in mapping the world laid the foundation for modern geographic sciences. While modern maps are far more accurate, relying on sophisticated technology such as satellite imagery and GPS, the basic principles Ptolemy introduced remain essential to the way we conceptualize space. Geographic Information Systems, GIS, for instance, rely heavily on the principles of latitude and longitude that Ptolemy first put into practice. In this sense, his geographical ideas have endured through the centuries and continue to shape how we understand and navigate the world today. The fact that Ptolemy's work transcends specific historical contexts and remains relevant in modern times also speaks to the universal nature of his intellectual approach. Ptolemy's methods were not confined to the particular cultural or historical context in which he worked, but have proven adaptable and useful across time and space. His integration of diverse knowledge, drawing upon Greek, Egyptian, and Babylonian intellectual traditions, demonstrates the interdisciplinary nature of his approach, which continues to be a hallmark of contemporary scientific and academic inquiry. Today, many fields of study emphasize the need for interdisciplinary collaboration, where knowledge from various domains is integrated to solve complex problems. Ptolemy's ability to synthesize a wide range of ideas into coherent systems of thought mirrors this modern emphasis on cross-disciplinary research. Ptolemy's legacy is also evident in contemporary philosophical debates about the nature of scientific progress and the limits of human knowledge. His work raises important questions about how scientific knowledge develops over time, particularly the tension between established models and new paradigms. The eventual rejection of the Ptolemaic system in favor of the heliocentric model illustrates how scientific ideas are not static. Rather, they evolve and change in response to new evidence. This dynamic nature of scientific inquiry is a concept that continues to be discussed in modern philosophy of science. How do we know when a scientific theory is no longer useful? When does it become necessary to discard a previously accepted model in favor of a new one? Ptolemy's work provides an important case study in this ongoing process of scientific evolution and the self-correcting nature of the scientific enterprise. Moreover, Ptolemy's place in the history of science contributes to broader cultural discussions about the relationship between science, religion, and society. In Ptolemy's time, his geocentric model was seen as consonant with religious beliefs about the nature of the cosmos and humanity's place in the universe. Even though modern science has largely dispensed with such theological interpretations, the historical connection between religious and scientific thought continues to be a subject of discussion. Ptolemy's ideas remind us that science does not exist in a vacuum, but is often shaped by the cultural and religious context in which it is developed. This recognition is crucial in contemporary discussions about the role of science in society and its relationship to broader cultural, religious, and ethical concerns. In the world of modern astronomy, Ptolemy's legacy endures not only through his methods, but also through the technologies developed in the wake of his work. The need for precise measurements of celestial bodies that he championed is still central to astronomical practice. Today's astronomers use instruments like telescopes and spacecraft to measure the positions of stars, planets, and galaxies with far greater precision than Ptolemy ever could. Yet the fundamental desire to map and understand the cosmos, which Ptolemy epitomized, remains unchanged. The tools and techniques may have evolved, but the intellectual curiosity that drove Ptolemy to explore the heavens continues to fuel the exploration of space. The persistence of Ptolemy's influence in modern popular culture also underscores the enduring relevance of his work. From the depiction of ancient astronomical models in film and literature to the continued use of historical references in educational materials, Ptolemy's ideas continue to capture the imagination. This cultural memory of Ptolemy's contributions highlights the lasting impact of his work, not just within the scientific community, but in the wider public consciousness. His theories, while no longer scientifically valid, remain an important part of the intellectual heritage that informs contemporary views of science and history. In conclusion, while Ptolemy's specific models of astronomy and geography have been largely replaced by modern scientific understanding, his broader intellectual contributions remain vital to contemporary thought. His methodological rigor, interdisciplinary approach, and emphasis on empirical data have shaped the evolution of scientific inquiry, and his work continues to influence fields ranging from astronomy and geography to philosophy and education. Ptolemy's legacy reminds us of the enduring nature of human curiosity and the ongoing quest for knowledge. As we continue to expand our understanding of the universe, Ptolemy's contributions serve as a touchstone, demonstrating how science evolves over time while building upon the achievements of the past. Through his work, Ptolemy showed that the pursuit of knowledge is a dynamic and ever-evolving process, one that transcends time and place, leaving a legacy that continues to guide our exploration of the natural world.